So, good news and bad news. I'll start with the bad news. I do not have your exams graded yet. There's more bad news. I also don't have the unit learning outcomes ready yet. I'll show you where I'm at with those. Unfortunately, with the exams, I had to be on a road trip on Friday, and so I got set behind on my grading, and I'm still trying to finish my OCHEM 1 exams. But there are fewer of you to grade for, so that makes it a little bit easier to catch up on yours. But there are more challenging things to grade on yours. Like the mechanism is really challenging to grade, and the synthesis is really challenging to grade. But I hope you guys noticed on that exam, the points were set to match the number of steps and like intermediates and reagents in the synthesis. So I'm hoping that that will speed up my grading a bit. This is where I'm at so far with the learning outcomes. I have not yet finished new reactions in section 19, and I haven't really gotten to start at 20 and 21. But we're going to come back and do more nomenclature in this unit. We'll have more things to rank as well. We'll be ranking reactivity of carbonyls and acidity of carboxylic acids. Good news is, I don't know if I have any good news. I hate to say that. Yes, sir.
So, John, did you change it?
Change what?
Your learning objectives from last OCHEM 2?
I've never made this before. You'll notice the verbiage is very specific. By the end of this section, students will be able to. So you can start each sentence with, students should be able to provide the correct IUPAC name. Students should be able to create a multi-step synthetic pathway. Students should be able to determine missing reactants, reagents, or products. I've never made anything like this. I've had like study guides before for my classes, and they are somewhat like this, except they are less descriptive. They don't have an action verb. It just says like, know the reactions for, and then just lists all of them. Know the mechanisms for, and then lists all of them. So I'm trying to be more descriptive here, and I just need to finish adding what reactions are needed. Yep. Any questions or comments or concerns about the exam? Otherwise, we'll just, if I do have them finished on Thursday, we'll spend some of our beginning on Thursday going over it.
Do you allow exam corrections?
I often do, yeah. So on the exam, I had bonus points, and I have found in the past that bonus points disproportionately benefit the people who already do well on the exams. Bonus points are not an equalizer. And I don't know that that's fair, so I've thought about just taking bonus points off. I actually saw a professor once that said he took off bonus points from his exams because students that have exam anxiety feel more anxiety knowing that there are even more questions that aren't actually worth the grade that they still can't answer. And so I've thought about taking the bonus problems off so that it alleviates unnecessary test anxiety, and just leaves the necessary test anxiety. But then I thought about my exam corrections, the exam analysis, which is not just corrections, but I ask you to reflect. Why did you get this wrong? Why was it wrong? Why is the correct answer correct? Don't just show me the correct answer. Explain it, master it. And that disproportionately favors people who did poorly on the exam. You earn up to half the points you lost. So if you lost 2 points because you missed one multiple choice question, you can get 1 point back. Great. But if you lost 20 points, you can get 10 points back. So you can see a greater improvement in your grade if you did worse on the exam. So I leave them now. I don't always market the exam analysis, But unless you guys average like a 90%, yeah, I'm probably going to allow it. Honestly, even then, the 90 is getting brought down by people that need it. So yeah, I will. Killian?
Are you going to go over the bonuses in class too?
We can talk about the bonuses Thursday, yeah. Or next Tuesday, if I don't have them ready Thursday. Any other questions? All right. A little preview about this unit. It is broken up to be 3 sections, 19, 20, and 21. Your textbook actually covers 20 and 21 kind of all at once. And I have found that trying to teach it as carboxylic acids and nitriles and then carboxylic acid derivatives just doesn't work for me. So I teach them all as one. And then the aldehydes and ketones, you'll actually see that there's components of all 3 of these sections that we're just going to cover all at once. And then we'll kind of specify aldehydes and ketones, and then we'll specify the other carbonyls. There are 2 written works for this unit. I think in the past, you guys have been used to just 1 written work for the unit. This unit has 2, one for aldehydes and ketones, one for carboxylic acids and derivatives. And we're coming back to the point where we have both mechanisms to learn and multi-step synthesis to show. So you'll be able to kind of take your pick at which one you want to do. Sorry, you have to do both mechanism and synthesis, but you get to pick a problem to do. All right. Unit 4 on carbonyls. I had a veteran OChem professor talk to me this semester, and he said that in his ideal world of teaching organic chemistry, carbonyls would be the first functional group you learn. In OChem 1, this is where you'd start. There's nothing inherently challenging about carbonyls compared to all the rest of the chemistry that you've learned so far. So just because it's showing up in the second half of OChem 2 doesn't mean that carbonyl chemistry is hard. It is arguably the most important chemistry in all of organic chemistry. But it's also widely diverse. There's a lot of different carbonyls, and they have unique chemistry, and we're going to dive into comparing their chemistry and understanding it. But because carbonyls are kind of a central point for a lot of different reactions, this professor would argue that they should be taught first. And then you can get into the boring and like more obscure things like SN1 and SN2 and alkene addition reactions and aromatic substitution. So it's an interesting perspective, and it's one that I'm actually going to consider over the next year. Our course lead for OChem is planning a retirement potentially in the coming year, which means that they may appoint someone else to be the course lead for organic, which is kind of big shoes to fill. And there's no right way to teach organic. There are best ways and more challenging ways. So I'm saying that all to kind of give you guys some control of this too. You get to experience organic chemistry, and you can reflect back on it and say, yeah, I wish I had learned that earlier. I feel like I would have been less frightened coming into other reactions later. So keep that in mind. Okay. We're going to rank out the reactivity of some of our carbonyls. And to do that, we're gonna get into all the different types of them as well. I think for this, I'm gonna have to spread out across more than just half of this board. I'm gonna have to skip this. Over here, we're gonna show our most reactive I'm saying highest electrophilicity. Anybody want to tell me, in your words, what a electrophilicity means? Electrophilicity Jones.
How deeply in love with electrons you are.
Yes.
Teenage romance.
How strong is the romance? Yeah. Or bromance, who knows? Electrons, we don't know their genders.
Up, down, man.
Out, down mates?
Up, down, man.
How strong? What?
Upspin, downspin.
No, I don't think it has anything to do with their upspin, downspin. And how strongly they love electrons? I agree. That would be a good definition or a translation of electrophilicity. But I'm not sure that kind of explains what they will do. How good they are at being electrophiles. We still got that term electrophile in there. So I want to see if we can substitute that to say more about what the chemistry will look like. You said how unstable they are as how unstable the cation that they form is. But they don't necessarily have to be cations.
How much they like to take electrons from other atoms.
Sure. Or accept electrons. How willingly they will accept electron pair donation. So on the left-hand side, we're looking at those things that readily accept electrons or are the most easily attacked by a nucleophile. Another way to look at this is your strongest partial positive. I would say partial positive over cation in general. We start here with the acid chloride. We know from our section on aromatic reactions that halogens have the capacity to participate in resonance. They have a lone pair that they can donate in to stabilize a positive charge on an aromatic ring during the sigma complex, which means that we can argue that this chlorine can participate in resonance with the carbonyl. It can share a lone pair to make a double bond and push a negative charge onto the O that takes on a positive charge itself. But it doesn't do that readily. In fact, we also know that the halogens create a lot of inductive effect away from the carbon. Remember that halogens in the aromatic reactions, they were deactivators because they pull electron density away from the ring. And they can stabilize the intermediate if it's positioned orthopara. But first and foremost, their inductive effect pulls electrons away. So this has a strong inductive effect towards the chlorine, which is already increasing the partial positive caused by the inductive effect by the O. So this has a very large partial positive.
Increase from right to left.
Yeah, we're getting to least reactive on the right-hand side. After acid chlorides, we have acid anhydrides. We're going to use acid anhydrides as a reference when we look at some of our other carbonyls. But I want you to recognize that the acid anhydride certainly has the potential for resonance. That lone pair of the anhydride linkage, that's what I refer to this as.
That's not technically an ester, right?
It is not an ester. Why? Why is this not an ester?
Because there's question actually. Because the right side has to be attached to the O, right? Well,
I mean, the right side is attached to the
well, I
other.
guess you're right. If you
Nir, you want to go?
I was just gonna say, because there's
Yeah, it's the presence of the two carbonyls. Esters only have one carbonyl. Okay, but why can't there just be a second carbonyl and we also call it an ester? Remember that functional groups are defined by their reactivity as well, right? The fact that a carbon-carbon double bond is not just an alkene, but can also be an aromatic ring, tells you that carbon-carbon double bonds behave differently in different situations. So the carbonyl to oxygen behaves differently if there's another carbonyl. So the presence of two carbonyls, that's what distinguishes it. And you can see the reactivity all the way on the left-hand side. Esters are actually going to be further over here, way further over here. They don't share reactivity at all. So here's a weird thing. The oxygen can participate in resonance with the carbonyls. Does it matter which carbonyl the oxygen participates in resonance with? No, it's either of them equally. But to a certain extent, it's one or the other. So the carbonyls don't necessarily prefer which will be electrophilic. So I'm going to have to just choose one to show you as being the more electrophilic carbonyl. But it's only one of the two. So I'm going to say, imagine that the oxygen in the linkage shares its electrons with the carbonyl on the right-hand side. This is already experiencing an inductive effect because of the CO polarity. And now it's having this kind of further inductive effect because the oxygen is pushing electron density even further away from the carbonyl. So this carbonyl gets a partial positive. Only one of them gets a partial positive, which means that the other carbon comparatively would get more of a partial negative, but we could also just write it as a much smaller partial positive. Which side does it need to be, left or right? Indistinguishable. It's one or the other. It's not both. Cooper?
Would the R have any effect on which side? If the R groups were different.
Very potentially, yes. And we'll actually look at how in aldehydes and ketones, we can look at that a little bit more. Yeah.
Does one of, how do you choose which oxygen? How do you know which oxygen pulls on the carbon's carbon?
No, you wouldn't. The oxygen would be split between the two of them, but if the R groups were different, then you could argue that one R group is impacting the partial positive of the carbonyl as well. After acid anhydrides come the aldehydes. How do you guys like to draw your aldehydes? With or without the hydrogen? Okay. I'm going to draw it in. The only reason I'm going to draw it in is because we know there's still a strong inductive effect towards the oxygen. In fact, I haven't been showing that, but there is this inductive effect towards the oxygen in all of these instances, which is to say that the generic carbonyl I'm just going to write Y. I can't put X because we usually say X is a halogen. And I can't put R because I want to just say, like, it can be anything. Your generic carbonyl always has this polarity, which means by nature, your carbonyl always already has a partial positive. Can we verify that with a second resonance form, by the way? Is there a resonance form that supports this partial charge distribution?
Pi electrons would go on the oxygen.
Yeah. Who owns the pi electrons, carbon or oxygen? Oxygen owns them. So we could look at this. Is this a favored resonance form? Why not? maximum charge instead of minimum charge. But it's a plausible resonance form, or at least it helps verify our prediction of this partial charge character. Now, we've so far looked at how the chlorine and the oxygen kind of have these inductive pulls away from the carbonyl, but the hydrogen, although small, has an inductive push towards the carbon. Hydrogen is helping to stabilize that partial positive a little bit more. Not much. It's still partial positive, but it is helping to stabilize it. It's that reverse inductive effect. Jamie?
Just like for my own list, for the acid chloride, we usually don't include fluorine, right? Because it's react differently than chlorine and bromine.
Okay, technically for the acid chloride,
Oh, cool.
we only put chlorine. For the acid halide, the most common acid halides are chlorine and bromine. I don't know that I will give you guys an acid bromide this semester. I know your textbook covers it, and it's like in one reaction in order to do one type of substitution. So it's like, we just don't get into it much. We're going to look at the acid chloride more than any other acid halide. Good question. After the aldehyde, what do you think comes? Ketone.
No one has just the one inductive effect.
Well, actually, this raises an important question. How is this R group impacting induction?
Depends on what fire.
Kind of, yeah. If that R group has a bunch of halogens, I guess it does have an inductive pull away. But if that R group is just carbon-based, then it has an inductive effect in. And so, in essence, assuming that the R group on the left is staying the same, and that we can negate that R group's effect on the left, by substituting Cl for now a carbonyl, for now a hydrogen, for now a carbon group, we actually get a much larger inductive effect in. And that's going to help to stabilize the partial charge even more. My partial charge, I've been trying to show it getting smaller. At some point, I'm running out of room. And we've got a lot more functional groups to go. So are you guys okay at this point? I'm not going to visually show the size of my partial positive. Does it matter that do I have to show it still? It's there. It's just, it's getting smaller and smaller. Killian?
How is it during induction?
Carbon groups have electron density that they don't necessarily pull on strongly. So having a nearby heteroatom means that their electron density gets pulled towards that heteroatom. This is actually the same process that we saw in OChem 1 with carbocations. Hyperconjugation. If I have a primary carbocation, if I have a methyl carbocation, CH3+, there's not a lot of electron density I can pull from those hydrogens. But if I have a tertiary carbocation, like the butyl carbocation, there's a lot of electron density in these groups that can get pulled in to help stabilize that positive charge. So electron density is, and actually we didn't talk about this with our alcohols very much. We talked about it in the review more so. But if I have a methyl alcohol, the oxygen doesn't have a lot of electron density to pull on. But if I have a tert butanol, then there is electron density from all three of those methyl groups. There's a lot more. Inductive effect is both a pull out and a push in, depending on what the group is.
It's the reasoning why more substituted is stable.
It is, yep.
How does induction differ from electronegativity?
Electronegativity tells you whether your induction is a pushing electrons in this way, or whether induction is a pulling electrons from this way. Chlorine, fairly electronegative, pulls electrons from the carbon. A carbon group, not very electronegative, has its electrons pulled towards the carbon as a result of the oxygen.
Okay. So the induction effect is still relative to the atoms in question
So you're using electronegativity to gauge the inductive effect.
How many more groups are there?
Ketone, acid, ester, amide, nitrile. I didn't count.
Yeah,
4,
that's fine.
5. After the ketone, we see our carboxylic acid. Uh-oh, did I make a mistake? How is it that I can have an oxygen connected to my carbonyl group, which makes it more reactive, and now I have an oxygen connected to my carbonyl group, which is supposedly stabilizing the partial positive more than the aldehyde and the ketone. This is a competition between induction and resonance. A resonance induction competition. Who do you think wins? Resonance wins. In fact, I mentioned with the anhydride, the resonance in one direction negatively alters the induction of the other, or enhances the induction of the other, negatively impacts the, I say negatively impacts the stability of the carbonyl. That'd be a good way to say it. Induction in one direction enhances the electrophilicity of the other carbonyl. Well, now there's only one carbonyl, and that oxygen can still share electron density towards that carbonyl. Is the OH, is the carboxyl group pulling electron density by induction? Yes. It still has this inductive pull. And at the same time, the oxygen is donating electrons back through resonance. So, quick question, what is the hybridization of the oxygen of the carboxyl group? General chemistry would tell us sp3. The fact that it's engaging in hybridization tells us sp2. You can't engage in hybridization or in resonance if you do not have a p orbital to participate with. So it looks contradictory because we'd say there's 4 electron regions, but we already covered that in aromaticity. We looked at how atoms will engage in resonance if they can and take on the hybridization that's necessary. So resonance, induction, competition, resonance has a more powerful effect here. After the carboxylic acid comes the ester. What difference do we see between the acid and the ester? Why is the ester more stable, a smaller partial positive?
Because the R group is less loose with its electrons than the H.
The R group has more electrons than the H. I think you could say actually the R group is less loose. H is less electronegative than the carbon group, but the H doesn't have a lot of electrons to give. A carbon group has more electrons to give. An OH group, the hydrogen is trying to give its electrons in that direction, but an R group gives even more electrons in that fight. It's again induction. The difference between, I know this flowchart is really full of information, isn't it? The difference between aldehyde and ketone was induction. That was our main piece. And now the difference between carboxylic acid and ester. It's the same difference as between aldehyde and ketone. You just swap out a hydrogen for a larger electron group, the R group. So you get more induction pushing in. Same amount of resonance, correct?
Yeah.
The oxygen is able to donate into resonance in the same way. It still has the inductive effect out towards the O, but now we're looking at how the hydrogen doesn't have much to give the oxygen. The carbon group has more to give the oxygen. Let me say it this way. Oxygen wants to share its electrons. Wants is anthropomorphizing it. Oxygen can donate electrons through resonance in both of these. Which group supports oxygen donating its electrons better? A hydrogen or an alkyl group? The alkyl group supports that better because the alkyl group pushes on the oxygen's electrons with more electron density.
So if it can support more electrons given towards the carbon, the R group, wouldn't it be swapped?
So remember, you can think of these electron groups as like magnets, right? Pile up more magnets next to the oxygen, and that oxygen is going to feel more of a push of its own electrons away from it. Not a lot of magnets here,
We swap.
a lot more magnets here. So these magnets are pushing on the O to share better, stabilizes the partial positive, makes it less reactive.
So because you can get more electron density on the ester oxygen, then it can, wouldn't that mean that you can allow a bigger charge in the middle on the carbon?
No, because the R group helps push on the oxygen's electrons, the oxygen shares them more readily with the carbon.
So it can give more to lower that positive.
Yeah. So it's as if the carbon has electrons more often. Here, the carbon has the electrons less often because hydrogen isn't really pushing on the oxygen to share those electrons. I do want to say something about terminology. I'm drawing dipole arrows. Dipoles are calculated things. They often come from the differences in electronegativities. There is a strong difference in electronegativity between O and H, and a smaller difference in electronegativity between O and R. I'm using dipole arrows here to talk more about electron push, less about actual dipole value. So this is maybe not a technical thing. What I might show you guys is like a electrostatic potential map, something that shows how the electron density around the carbonyls differs depending on what groups are surrounding it. I'm just not sure if I'll find a good electron map for that.
What are the two groups after ester?
After ester, we've got amide. Sorry?
Then it's amine, what is it?
No. After that is nitrile. Now with amide, I'm going to leave this as NR2. But I want you guys to recognize it could be NH2, it could be NHR, it could be NR2. That is primary amide, secondary amide, tertiary amide. And as you increase from primary, primary is more reactive than secondary, than tertiary, because you're getting this inductive effect. The more R groups on the nitrogen, the more the nitrogen stabilizes the carbonyl, the less reactive the carbonyl is. Is there induction from the carbonyl towards the nitrogen? Is there this same dipole? Is there a polar bond between C and N? There is a polar bond between C and N. It's a less polar bond. C and N are closer in electronegativity. It's a difference of 0.5. So it's not a very strong induction. But what else can this nitrogen do? It can pull electrons from the R's. Resonance. The nitrogen shares its lone pair through resonance to the carbonyl. Do you think nitrogen shares its electrons better than oxygen, or do you think oxygen shares its electrons better than nitrogen? You didn't have to guess. You learned this already. What?
But oxygen has two lone pairs to give.
It can only give one. Only one of them can be in a p orbital. The other is in a hybridized orbital.
Is it because the oxygen pulls stronger on its electrons that it's...
It's because oxygen is more electronegative, less likely to share. Nitrogen is less electronegative, more likely to share. So this isn't even so much a fight between resonance and induction, because the induction is much smaller than with the carboxylic acid and the ester. And the resonance is much stronger than with the carboxylic acid or the ester. And then our last group. This is sometimes not considered a carbonyl, but it has the same oxidation state as a lot of these other groups. So it's grouped in here with a class of reactions, and that's the nitrile. You guys also know the nitrile as the cyano group. Yep.
And here is the alkyne electron resonate into the nitrogen.
No alkyne.
Oh, because it's not C to C.
Yeah, no C to C triple bond. No, there's actually no resonance here. There is no resonance within this one. I'm open to hearing you guys discuss your opinions. Why do you think the nitrile is the most stable? Why do you think the nitrile has the smallest partial positive? Why is the nitrile the least reactive?
Because of the strength of the triple bond.
Triple bond strength. You know, there's two different ways to look at that, which is the pi bonds themselves are fairly weak. The pi bonds are not necessarily any stronger than these pi bonds, but you've got 3 bonds to have to break through. That's where we say a triple bond is strong. You're calculating the breaking of all 3 bonds. So no, I don't think I'd say it's because of the strength of all 3 bonds combined.
There's no oxygen involved, and we just talked about how nitrogen is less electronegative.
Yeah, we said the carbonyl assumes this template where there's always a dipole towards oxygen, and this actually has no oxygen. I'm going to write this as has no dipole towards oxygen. Since the nitrogen is less electronegative, any partial charge on the carbon will be a smaller partial charge than if there is any oxygen present. All right, now within a group, we can say when substitution increases, electrophilicity increases. This is as simple as looking at acetaldehyde versus propanal versus isobutyraldehyde, and this tert-butyl methanal or tert-butyl formaldehyde or 2,2-dimethylpropanal. Oh, I'm sorry. I wrote it wrong. We have to flip one of the two arrows. It actually doesn't matter which one you flip. I think it probably makes more sense to say when substitution increases, electrophilicity decreases. There's another one I should have added too. I'm so sorry. It's on the far left side. Formaldehyde should be here, then acetaldehyde. A methyl aldehyde, a primary aldehyde. All aldehydes are primary. A primary aldehyde with a primary carbon, a secondary carbon, a tertiary carbon, a quaternary carbon. So we're not even looking at the substitution of the carbonyl. We're looking at the substitution of the neighboring groups. As we go from hydrogen to primary carbon, to secondary carbon, to tertiary carbon, to quaternary carbon, those groups are able to induce electrons towards the carbonyl to stabilize it more. Can you tell me which side of this chart is most reactive, most electrophilic? Left side. Most reactive, least electrophilic. I'm not going to take the time to expand onto that because we can say the same thing with ketones, but now it gets more complicated. Both carbons are primary. One is primary, one is secondary. Both are secondary. One is secondary, one is tertiary. All of those possible combinations. The same thing goes with acid halides, anhydrides, carboxylic acids, esters, amides. And we've already considered how when an H is substituted by an R, that is increasing the substitution, decreasing the electrophilicity as a result of induction. We're not going to see so many examples where reverse induction is relevant, but we could say as neighboring electronegative atoms increase, electrophilicity increases. If I place more fluorines nearby, partial positive increases. It's just not something that we see as common. So I think I made the sheet wrong. At the top of the sheet, you'll see name the compounds below. We haven't gone through naming yet. And at the bottom, it says pick 5 and rank them by increasing reactivity, increasing electrophilicity. So I'd like you guys to do that right now on your own over the next 3 or 4 minutes. I want you to pick 4 of those compounds. And then think about what order they're going to go in. And then I'm going to have you pair up. And you're going to swap compounds and rank the other person's choice. I want to make sure I make it clear. You're going to pick 4 compounds. Don't list them out necessarily on your own, or at least don't show that to your partner later on. You're going to pick 4 compounds. Your partner is going to pick 4 compounds. Think about what order they should go in. And then you're going to swap those compounds and make your partner rank them. So maybe you go through and you just label them A, B, C, D, and then later you give them to your partner and you say rank these 4. Is this okay? Can I be more clear about my instructions? Let's take 3 to 4 minutes. Just pick. Did I say 4 or 5? Let's do 5. Pick 5 compounds that you want to rank. I'm giving you 4 minutes to consider this because I want you to be able to apply these trends. Yeah? And think about ones that would be worthwhile ranking. Then you're going to swap. not isobutyl. You could call it isobutyraldehyde. There's a weird YR part in there. Isobutyraldehyde.
Like pewter? Isobutyr?
Butyral.
Butyral. Butyral. Yeah. So off of a ring, that would be called isopropyl?
Yes, but there is a fourth carbon. So the whole compound is an isobutyraldehyde.
If instead of the aldehyde, it was a ring, then it would be.
Yeah, that is an isopropyl substituent.
It's weird.
And actually this, let's say like that was a group. This is a ring. That's an isobutyl group. There's 4 carbons. If you guys are ready, feel free to find a partner, but no rush yet. You know, it's up to you how you want to do it. You could swap your papers, or you could just write down what compounds on your own paper. Make it a game. Have fun with it. Whatever works better for you. Are you 3 working as a triplet? Kind of rotating? Great. I'll work with you. Do you agree with that image up there? That the structure on the right is more blue?
I disagree with the image.
It does look more blue. It looks more blue on the right.
think you're
Yeah.
saying specifically the carbon is more
Yeah, I mean, if it's pointing, yeah, I guess if you're looking at the carbon, no carbon is more blue. But as just like a quick glance, it's like the structure on the right just looks more blue in general than.
without context.
I feel like this region looks more blue than like this region. But I guess, yeah, I wasn't really looking. The carbon sits higher up in the green,
Yeah.
and it sits lower down in the blue here. But I feel like the difference is almost too small.
Yeah. Like I said, at a quick glance, you're just like, oh, it's just more blue and just
Yeah.
like.
Yeah. Okay, I'm gonna give you a random 5. I want you to do it. Okay. I want you to compare. I'm just gonna give you 5. You want to tell me what 5 you picked?
Yeah, I did.
Mm. Okay, got it. It's hard. Mm-hmm. So how do you guys feel?
My match the Cooper, we just switched, I just have my senior. So I put my ketone over the aldehyde, but but yeah.
Mm,
I
okay.
figured that we matched.
You said the ketone was more reactive than the other. Okay. So how did you guys do it? Did you just pick 5 compounds as a group?
Or randomly.
Oh, you swapped.
Yeah,
Okay.
then I just matched what I got for substitution.
How did you decide to pick the 5? Did you just like
Well,
me,
I thought it was more reactive, so I guess.
Oh, okay.
I wanted it to affect.
Sure. Okay. Because it is easy if the only difference is the functional group. It's a lot harder if you have 2 of the same functional group and you have to decide between
Yeah.
the substitution.
Yeah,
groups. Okay, so you said this one is more reactive than this one, right? Or did you say that? Okay. Okay. And how would you compare these? Because they're almost identical except for an alcohol. What was your research? Yeah. So there's actually you can push more in, and that's going to stabilize it more. I guess I am a little confused. You're saying this is the most reactive, least reactive,
I guess
followed by this. Oh yeah, because then you've got 3 aldehydes. Later this one.
I read it. I was
The least reactive, then this is more reactive. So I would actually swap those. This one should be less reactive because, like you said, it has more resonance coming in stabilizers. And then I would say this one, although it depends on which carbonyl you look at. So the aldehyde here has a tertiary neighbor. Aldehyde here has a secondary neighbor. So I would have said A, B, C, D. This is the second most reactive. And then this is the by far the most reactive. Most reactive, second most reactive. Third, E and C. But that would be a challenge to say like, is it the substitution or is it the or the resonance? Good work, guys.
Thank you.
What do you guys think?
Pretty good.
Okay.
we're in agreement now.
How did you decide to pick the compound?
I was trying to do the opposite, but I kind of failed. I was trying to pick the same functional group, but I don't think that resonance. End up with 2 ketones.
Just 2 ketones were in common and everything else was different?
I was like, this is
If it had another carbon, it's a ketone.
I'm just
All right.
imagining it as one of those like.
Now, these 2 would be challenging, right? Because they kind of have the same substitution on it. Oh, no, I guess second secondary, so we think less electrophilic and primary, secondary.
Yeah.
But this actually has resonance. This can donate resonance up, which I think is going to decrease electrophility more. Is that what you guys said?
This would be the least reactive, and then B.
No, I mean,
Good. Okay, yeah.
most of
Least
these
reactive, second least, then
Why do you do that?
then yeah. Great. Good job. And what did he give you? Or these were the ones you picked?
Yeah.
Acid chloride, anhydride. Ester, amide, nitride. Good. Very well. Excellent. I'm so sorry. I ran out of sheets. Yeah, you don't need it? No, I took a picture of it on here. We just finished up talking about how to rank reactivity. And we did this part. But we're going to move into the nomenclature part. Thank you.
It's kind of very clear right now. It's kind of
Yeah. How would you rank those two? I would
I would say that this one has more resonance.
less resonance. This actually has a double bond that can share electrons with the oxygen. This has no resonance.
I thought the resonance was
Not to the ring. No. Resonance has to be an uninterrupted series of sp2 hybridization. So this one actually can push electrons all the way from the ring. Yeah. So your least reactive, followed by the ester, followed by the acid, followed by the aldehyde. Chloride is the most reactive. Yeah. Great work. And what did he give you?
That was his set. Mine was just the second one in every row.
Okay. So aldehyde, ketone, acid anhydride, ester, nitride. Great. What'd you do?
I did this. It is my check.
Most reactive?
The most reactive.
Mm. Here you've actually got two carbonyls, but the aldehyde would be more reactive than the ketone. And then this ketone is still more reactive than this ketone. And then the amide. Now this, I would argue.
So this
Probably, yep. This one is probably here between these two compounds.
so
Because
this
it's still
is
an
more than this.
aldehyde.
I know this one is more than this, eh?
Yeah, this is more reactive than this. But this one, the amide is in resonance with the nitrogen and shares better.
So this is swapped. Or is this?
Yeah, I mean I don't know the exact numbers, but I would argue probably the aldehyde is still more reactive here than the ketone is. Yeah. I know.
Look how far away that is.
Well, the pi bond is there.
It's gonna walk 3 down.
Well, what you're saying sounds like you're supporting my idea of putting it here.
No.
It made it sound like you were saying, why would it participate in resonance?
Yeah.
Yeah.
I did say that.
Yeah, he did. These two are swapped. This is no least reactive. And it's right there. It's their neighbors.
I was like wondering if
Question. Alright, yeah.
how close they were on the scale.
Let's talk about that. Actually, there's one more story. What'd you give him? He gave me blue. Okay. So least reactive. Yeah. Followed by the
Oh yeah, like
carbonyl acid.
my cousin
Least
has
reactive.
that
Second
one.
least reactive.
Even though the person
This
was
is the most reactive. Okay.
and he has
The acid
something
chloride
like all the stuff.
on the far left side of our. Oh yeah. Far left side of our function. Yeah. Acid chloride is the most reactive. Nitriles on the far right side. And then, so actually you can base it just on functional groups, but you've got two aldehydes. So the aldehydes we'd have to use within a functional group. Since this has a quaternary carbon next to it, and this has a secondary, this should be less reactive. This would be more reactive. Less reactive, more reactive. So it would go acid chloride, quaternary neighbor aldehyde, secondary neighbor aldehyde, and then carboxylic acid. And you gave him these ones? Yeah, I gave him circle in red. And what did you say?
Yeah, I'm so shocked.
Give me the most reactive.
Yep. Like just right now. And you can update it. I didn't know there was.
What'd you do? Here, look at your paper.
So the challenge is between the two carboxylic acids. And you need to do I would have maybe looked at the resonance. The fact that this alkene will actually donate electrons towards the carbon as well. And that resonance is going to help stabilize it. So I want to talk about the resonance for a second. Okay, so to recap on this exercise, the compounds I gave you weren't necessarily as neat and easy as pick the functional group or pick the substitution, because there were a number of them that had resonance in there as well. So I wanted to discuss how resonance might change within a functional group and what resonance might do between functional groups. So for instance, if you had a carboxylic acid versus a carboxylic acid that's conjugated to an alkene, or similarly, if you had an alkene versus, or an aldehyde versus an aldehyde conjugated to an alkene, the alkene can actually push some of its electrons towards the carbonyl in a similar way to how the oxygen can. Carbon might not do that as readily. The reason being, when carbon participates in resonance, it not only maximizes charges, it also minimizes octets. One of the compounds on there is cinnamon aldehyde. OChem 1 did the essential oils lab this week, so I thought I'd bring this back in honor of that. And the cinnamon aldehyde could push electron density all the way from within the ring. But anytime a carbon group is pushing electron density away from itself, it's going to break an octet. Whereas when an oxygen group shares electron density, it doesn't break any octets. It just creates charge. So in those examples, I'm not going to give you one that's that challenging, that says like, should an aldehyde with an alkene next to it be more or less reactive than a ketone, since those are neighbors in reactivity anyways? Does that push the aldehyde past the ketone, or does it keep it below the ketone? I think that's kind of an arguable spot and not one of the key things I want you guys to lean into. I'd rather you be able to tell the difference between substitution than actual impacts of resonance. Remember, in resonance, we saw that phenols are more acidic than alcohols because of resonance with the carbons in the aromatic ring. And yet, despite having more resonance forms, the phenols are less acidic than carboxylic acids. Less resonance forms, but more oxygens holding the negative charge. Resonance is a strong factor. Induction is another factor. And it's hard to separate their effects. They have compounding effects that are constructively and destructively interfering. There was one other thing I wanted to mention about induction. We said that the aldehyde is more reactive than the ketone because of this inductive effect. But you can also look at that and think about sterics. There's higher steric strain around the ketone. That gets less and less true for our carboxylic acid and ester or your primary, secondary, tertiary amide because the sterics is further away. But in a way, the sterics is the inductive push to help stabilize the carbonyl. The ketone certainly has more sterics than the aldehyde. And so if induction between aldehyde and ketone is challenging for you to grasp, then you can try to think about the sterics between the aldehyde and ketone. I found this image to try and show you the electron density of the carbonyls and show that the aldehyde is more electrophilic than the ketone. I feel like it doesn't make its point very well. I feel like the colors are so similar, it's hard to believe. But when I looked at it a little bit closer and noticed, oh, where the carbon sits in the color, this carbon sits lower down into the blue region, and this carbon sits higher up into the green region. And that, you can kind of feel the effects of the sterics. These large groups are sitting here blocking entry to the carbonyl. Granted, carbonyls are flat, so they get attacked from the top or bottom anyways. But there's even more crowding above and below this carbonyl than here where it's just hydrogens. I couldn't find any electron density maps with other functional groups, unfortunately. All right, any questions on this reactivity trends portion? All right, why don't you guys take a break? Let's come back in like 5 and we'll talk about nomenclature. Anybody need this up still?
Have you done any OChem 2 test yet?
I've not graded any of them.
Any OChem 1 test yet?
Yeah, I only have 10 OChem 1 tests to finish, and then I'm done.
You haven't graded them.
Yeah. Give everyone their exam back.
Okay. Oh, my phone's gonna go.
How you break your phone?
Actually, one of my OChem 1 students has accommodations to test virtually. So somebody hops on Zoom with them and tests, watches them take the test on Zoom. Which is kind of like, I've done that before for students. Just pull them up on Zoom and I'll talk to them over Zoom. And the testing center emailed me their exams, or the images from their exams, right? And said, by the way, like this one page was sent to us twice. Once originally with everything, and then once later on in the night, just that page. And the student said, I forgot to include this. And they originally said they compiled it all into like one PDF, all the images. And they said the first page was what they sent first. The second page was what they sent later in the night. When I graded it, the first page, completely right. No errors. The second page, not completely right. Like half right. And I was like, you're telling me that they sent a picture of the page that they screwed up on later on in the night? Why bother? Well, benefit of the doubt, maybe they had done that page, came back to it later in the exam, redid it, and then said, like, oh, I should show my work of the wrong answers. Or maybe they came back to it later in the exam and redid the whole thing, and then forgot which one to take a picture of. But like, you sent a picture of a page later on after the exam ended, and all of the answers were corrected, that's way too suspicious. I can't grade that page. Ultimately, it did not change the letter grade. The letter grade was not good. So it doesn't make a meaningful impact which page I grade. But I can't. I can't get the page that was submitted hours later and fixes all these corrections. I feel bad. What can I do? They never come to class, so I can't talk to them in person. I can write them an email. They don't respond to me usually. In fact, this student even emailed me and says, my work doesn't let me take off for our exam day, so I need to take it October 30th, which is like this Friday. And I was like, that's really far away. I'd rather you take it much sooner. And I was like, what's your work schedule look like? I'll work with you to find a time where I can proctor it. And then one day, I just got this email. Here is your student's exam. Okay. They figured it out. So weird. Wow. I'm all about giving the benefit of the doubt. But that is just a little bit too much of a stretch. And if it comes down to those like 6 points later in the semester, maybe we can. I don't know. You know what? It's just more for them to earn back through test corrections, the exam analysis. Truly bizarre.
Yeah, it's really bizarre.
Situation.
They had it right the first
I
time.
think you did right.
Right the first time or wrong the first time?
I don't know. Because actually, originally they said the first page was the one that they sent originally. The second page is the one they followed up with. But the second page was the one that was wrong. So I emailed them back and I was like, can you confirm, was it like this page described this way or was it this page described this way? And they said, oh, it was this page, the one that was wrong that they sent in originally. And then it was, so they had told me it wrong, which page was sent in originally. It was the one they sent in originally had the errors. It just makes me think they turned in the wrong, and then they turned it in and then went back and reviewed it and was like, oh, I was so off on that. I fixed all of them. And then he was like, I just forgot to submit this. Yeah,
That far after you think something suspicious happens.
well, then I don't have a timestamp.
Okay. It's like 5 minutes past 1 p.m. and it's like 5 hours.
Do you think I should email the testing center again and ask, like, what are the timestamps on the email? How long after was it?
Yeah.
They described it as later on in the night. But I don't know.
Yeah, I'd probably get
Was it
how far, if it was like,
Was it
It's
5
like-
minutes? They couldn't have fixed it in that
Yeah.
time.
I'd
It was like 3 hours or
emails,
something.
like screenshot the timestamps, like I want to be able to read through what they said.
That's fair. I think that's fair. And it shows that I'm doing the most that I can, right? I'm leaving no rock unturned. I'm not making any assumptions. I'm looking at all the data. Yeah, I should ask for that. Anyways. Okay. There was something I actually wanted to say all at the front before I just like got into this whole thing, but I'm kind of glad I didn't because I really needed that whole board to rank all of these. We said that carbonyls are electrophiles. And because of that, all carbonyls can go through acyl addition. Depending on what the carbonyl is, the acyl addition can look different. Sometimes acyl addition is followed by, you might call it acyl elimination. It kicks off a group. Sometimes it's not. But carbonyls can also be nucleophiles. I mean, in the sense that they are bases. What we typically look at here is how the oxygen of the carbonyl is weakly basic and can accept protons. It's not incorrect to say that the oxygen of the carbonyl can attack other types of electrophiles, but the oxygen of a carbonyl is not a strong enough nucleophile to attack even the carbon of a carbonyl. So we won't see any of this like polymerization between the oxygen of one carbonyl and the carbon of another carbonyl, but they can become protonated. And we're actually going to see how this is useful. The partial positive of a carbonyl, we've considered how to rank. But the partial positive of a protonated carbonyl is even stronger. This process increases electrophilicity. Anybody want to try and argue why this process increases electrophilicity?
Less electrons to balance the positive on the carbon because the positive on the oxygen gives less electrons to the carbon.
You're trying to say the oxygen now is even more greedy for the shared pi electrons? Seems like no, that's not what you were trying to say, but these other guys agreed with it. Oxygen shares these electrons, but it owns them, it pulls on them. Now oxygen wants them back bad. It's got a positive charge. Give me my electrons. Increases that polarity towards the oxygen, increases that partial positive charge.
Yeah.
Earlier, we said that the carbonyl has a resonance form where oxygen is negative and carbon is positive. And we said it was not a good resonance form. Breaks the first rule. It maximizes charges. And it breaks the second rule. It breaks octets on the carbon. But here, I actually have another resonance form which does not break the first rule. It only breaks the second rule. Charges stay the same, but octets are still broken at that carbon. So that might be a way that we can argue electrophilicity is increased in the protonated state because the resonance form is kind of more valid than the resonance form of the deprotonated state. So we'll take advantage of that. For those carbonyls that are not very reactive, we'll protonate them first if we need to react with a weak nucleophile. We'll increase their electrophilicity by protonating the oxygen first, and then we'll introduce a weak nucleophile. All right, any questions? Okay, let's get into nomenclature. We're going to start by looking at suffixes.
Where did you learn to differentiate a group as a Y group?
I don't know. I don't know a lot of things. I have also seen them as like Z groups as well, but I don't like the Z as well. As much. All right, we're gonna kind of keep our order of reactivity. One of the reasons I like to do that is just to further ingrain it in your head, the order of their reactivity. So for our acid chlorides, there's a new abbreviation of the acid chloride, RCOCl. The suffix becomes oil chloride. Maybe I should have reminded that we actually are naming suffix stoppers. Shoot, I didn't really say that. That's because you won't find that in a textbook. That you'll only find on johnfloodchemistryyoutube.com. We always have to provide a stopper of its own, a suffix of its own, and then we can stopper that suffix with one of these. So, to backtrack a little bit, we get these options of ane, een, ein, but we can also have een, ein. Those are our suffixes. And when these get stoppered, they become ane something, een something, ein something, oops. Or they become een, ein something. We're taking that E off of the suffix and we're putting on something new. So now I get something like benzoyl chloride. So here's a good example. If I have the benzoic acid, benzene substituted by an acid chloride, so it looks like benzoic acid, but it's the acid chloride. In the same way that I take benzene and I make benzoic acid, this gives me benzoyl chloride. Let's look at another similar one, but one that has a more common root. A butane chain with an acid chloride. Butanoyl chloride. Honestly, that's a terrible way to write. You know what that is? That's got to be the anhydride because we're doing order of reactivity. I feel like that doesn't convey anything, to be honest. So let's find a better way to write it. Still kind of abbreviated, but it would be much harder to type this. The suffix we get here is oic anhydride. Let's look at something that is a symmetric anhydride. That means that the two R groups are the same. Here I've got benzoic anhydride. And if I have something that is asymmetric, here I've got a benzoic side of my anhydride. I've got a propanoic side of my anhydride. I name them both alphabetically. Benzoic, propanoic, anhydride. You should notice that benzoic is the same name we give to benzoic acid. And that's because this is the acid anhydride. 2 equivalences of acid combined. If I had 2 equivalences of benzoic acid and I dehydrated it, I'd get benzoic anhydride. But here I have a benzoic acid portion, a propanoic acid portion, so I get benzoic propanoic anhydride. Aldehyde gets the suffix stopper al. This is a compound that we're going to learn how to synthesize in Unit 5. What is the longest carbon chain? What's my root for this compound? Pro. And the suffix? -ene. And the suffix stopper? -al. So this is propanal or propanal. Locants are still at play here, but this compound is so small there is no other structural isomer possible, so locants aren't necessary. But if I had a longer carbon chain and my alkene was further away on that, I would need to describe where the alkene is by giving it a locant. Conveniently, the aldehyde never needs a locant because aldehydes are a higher priority functional group, and so they always get numbered as position 1, and you count from the aldehyde. So we know the aldehyde is at position 1.
Where do we? Isopropanol? You have isopropanol?
Isopropanol, where there's a
Or would that be
carbon coming off of this.
isoethanol? Yeah, off the middle.
Look it up. Tell me what you find.
Would you say that most of these carbonyl groups would be like high priority in their locants?
We'll talk about how to prioritize them individually, yeah, or against each other. Ketones get the suffix -one. I always think this is funny. The aldehyde gets the suffix from the start of its name. The ketone gets the suffix from the end of its name. What is the longest carbon chain containing the ketone? No. 3. This carbon is a part of the ring, which means that it cannot be part of a linear chain as well. Remember that parent chains are either rings or chains, but they cannot count carbons from both a chain and a ring. So I have a 3-carbon chain, and so the question is, should I number from the left or should I number from the right? Here I'm going to number from the left because then my cyclopropyl substituent gets its lowest position. So I'd call this 1 cyclopropanone. There's really only one place the ketone can be on propanone, but otherwise I might need to name where the alkene is. Here's another ketone. I'm going to put an alcohol on here so we can discuss that priority factor again. In OCHEM 1, alcohols were the highest priority functional group. Make sure you start where the alcohol is and number towards it having the lowest locant first. But alcohols are not our highest priority anymore.
Let's go back to the 1 foot ring.
Yeah.
It just seems, I mean, is there, I get the cyclo, like, it's a 3-numbered ring and it's 3 carbon linear chain.
Oh.
But aren't we missing?
I screwed up.
Okay.
Yeah.
It's like, I don't think that's specific enough.
How would you fix it, Cooper?
I guess I'd go 1 cyclopropyl propanol.
Yes, you're exactly right. 1 cyclopropyl propanone. Thank you for spotting that. I merged them and I did not mean to, but they both had that prop root. 1 cyclopropyl propanone. Alcohols are no longer our highest priority functional group. Here, we actually will find that alcohol will not be named in the suffix. It must be named in the prefix. And we're going to aim for the ketone having its lowest priority, or its lowest locant. If I number from the left, the ketone is at position 3. If I number from the right, the ketone is at position 4. So I'll number from the left, which gives me 5-hydroxy hexane 3-one. Or you can move that locant to the front and you can call it 5-hydroxy 3-hexanone. We have to use the locant to describe where the position is, because the ketone could have been on position 2, 3. Actually, that's all. It could have only been on positions 2 or 3. Carboxylic acids. Oh. I stopped using my abbreviations. CHO for the aldehyde. O in parentheses for the ketone. We already know the carboxylic acid gets the suffix oic acid because we've already named benzoic acid. This compound gives us an alkene as the suffix. And because the carbon chain is longer, I have to describe where along the carbon chain the alkene is. Should I number from the left to the right, or should I number from the right to the left? Good. What's another way of saying that? I'm going to number from. Good. I'm going to number from the carboxylic acid, the highest priority group. So my alkene starts on position 3, and I have a 5-membered chain. This is pent 3-ene-oic acid. Or, because there's only one locant I have to worry about, 3-pentenoic acid. You guys are caught up on this side? Okay. How come I don't need to describe where the carboxylic acid is on that chain? It's gotta be carbon 1. It's a terminal functional group, so it has to be there. All right, the ester RCO2R. This actually gets this is a bit confusing. It needs a prefix of whatever alkyl group is on the OR side. and then it gets the suffix O8. O8 is actually the same suffix that we give to the conjugate base of the carboxylic acid. Carboxylate gets the suffix O8. And so we're basically naming this as an alkylated carboxylate. We'll say methyl benzoate, or we'll say ethyl acetate. Here is what we'll name with the alkyl portion. I call this the ester linkage. We're naming the alkyl group connected to the ester linkage. So the start of this compound's name is isopropyl. That's kind of the prefix of the compound. Then I'd have to name any of the substituents that are going on inside of that parent chain. I don't have any substituents. And then I get butanoate for that 4-carbon chain.
Why is the ketone not 2,4? The hydroxyhexanone. The one beneath no, yeah.
2,4.
Yeah, why not 2,4?
Oh, the ketone is the highest priority. I need the ketone to have its lowest locus.
Ketone's higher than alcohol?
Mm-hmm. The carbonyl is. For amides, we actually get a prefix that goes N-alkyl. We specifically say that whatever the alkyl group is connected to the amide linkage is connected to the nitrogen of that. So we say N-methyl, N-ethyl, or we say N-dimethyl, N-diethyl, if there are two. And then the suffix is nice and simple, amide. Okay, so in this compound, I've got 2 nitrogens coming off of there's 2 methyl groups coming off of the nitrogen of the amide. So this will have to start with N-N-dimethyl. Then I can describe the substituents off of the parent chain. And I'll name it 2-methyl propanamide. Yeah? I've got this 3-carbon parent chain, and off of carbon 2, I've got a methyl group. All right, the last one is the nitrile. Whatever. In the nitrile, we give it the suffix nitrile. True or false, the carbon of the carbonyl is counted in the parent chain for all of these other functional groups.
Yeah.
True, we count the carbon of the carbonyl. So we will also count the carbon of the nitrile in the parent chain here. hang on. What is the longest carbon chain containing the nitrile functional group? It's just 3, yeah. Where do I number from, the right or the left? Yeah, where the nitrile is. So off of carbon 3 in this compound is a cyclohexyl group. 3 cyclohexyl Do you know what is, we have to put the E back in, because we can't just put NN, so we're going to say propane nitrile.
That's what IUPAC says.
Mm-hmm. I'll be honest, the nitrile is the one I have you name the least, because its names always feel the funkiest. Okay, so I did forget to mention, but in order of your priorities, we have the carboxylic acid and the ester. I'm not going to have you name a compound that has both, so I would say it's better to consider them as tied. They're both on that higher priority side. The anhydride and the acid chloride, those are also pretty high priority functional groups. I'm not going to have you name a lot of them that have any other type of functional group. It's just going to be that suffix on them. So I'm going to 1, 2, skip a few, and we're going to say that the next main groups I'm going to have you name are the anhydride and the ketone. Technically, the carboxylic acid is a higher priority functional group than the ester. Like I said, I'm not going to have you name a compound with both. But the aldehyde and the ketone are tied legally. But in the case that both are present, who gets priority? Alphabetical is typically the way it goes. And aldehyde comes first before ketone. But actually, it's whichever one will always have the lowest locant. And the aldehyde will always have a lower locant than the ketone, because the aldehyde is a terminal functional group. It will always start the carbon chain. So this one wins in a tie. After these functional groups is when we see the alcohol, and then we see the alkene and the alkyne. That's why alcohols are actually showing up as suffixes. No, sorry. Alcohols are showing up as substituents. They're showing up in the prefix because alcohols no longer have the priority over the suffix. The other thing I wanted to give you is that if an aldehyde and a ketone are both present, they cannot both go in the suffix. Only one goes in the suffix. The other has to be named as a prefix. So the aldehyde and ketone substituent name is oxo. They're both oxo. So if you have an aldehyde and a carboxylic acid in your compound, oxo for the aldehyde, oic acid in the suffix for the carboxylic acid. If you have both an aldehyde and a ketone, oxo for the ketone, al in the suffix for the aldehyde. Yeah. Aldehydes and ketones are named as oxo if they are too low of a priority. So if your compound has both an acid and an aldehyde, you can't put both of them in the suffix. The aldehyde has to be named as a substituent. It's lower priority. If both an aldehyde and a ketone are present, they can't both be named in the suffix. Aldehyde wins in a tie. Ketone is named in the suffix. And they're both named oxo, which I think is kind of cute. And you can name a compound that has both an aldehyde and a ketone and a carboxylic acid. 1, 2, 3, 4, 5. This is 3,5-dioxo pentanoic acid. I think that's a good way of summing up how they both get the same functional group, or the same substituent name. All right, I've taken you guys over time. I appreciate your time. I encourage you to work on that worksheet between now and next class and get a head start on all of the upcoming homework and look for the nomenclature. Look for the ranking the reactivities. When we come back on Thursday, we'll take a look at some of these compounds and we'll name them together. And then we're going to move into reactions with aldehydes and ketones. All right. Have a great night, guys. I'll see you on Thursday.
What is the abbreviated amide?
Amide as a substituent?
Just the like abbreviation, like you did the R.
Oh, you know what? I didn't.
I want to
I even laughed when I
forgot it.
got to nitrile because I was like, I didn't do the amide. It's harder to do. I think I'd probably do this. Yeah, it's similar to what we did with the anhydride.
Can I ask you a question on the aromatic substitution report?
Yeah.
I was going back through and seeing what I can still get points back on.
Yeah.
There's a few points I can get back on that one.